For this experiment, you will need a power supply, an electronic balance, an ammeter, a Pasco current balance apparatus, a retort stand, and a number of wires to connect everything up. Now, this Pasco current balance apparatus consists of a bracket that is mounted on the retort stand, and on the end of the bracket is a small printed circuit board, and this printed circuit board contains the wire that we use in the experiment. The apparatus also contains permanent external magnet, which consists of actually 6 smaller magnets. In part A of this experiment, we are going to change the length of the wire in the external magnetic field and measure the deflection of the magnets. The Pasco current balance apparatus comes with 6 different lengths of wire, and we will start with the smallest length first, which is on this printed circuit board. Remember, it's just the bottom section of the wire that's in the external field that we will be using. Now I'll place a centimeter scale up against this, and you can measure the length of each of the 6 wires. So in trial 1 of the experiment, we will be using this wire, and you can see from the centimeter scale placed along it that it is 1.2 centimeters long. Now here's the wire we'll be using in trial 2, and with the centimeter scale placed on top of it, you can see the length of the wire is 2.2 centimeters. Now here's the wire for trial 3, and again with the centimeter scale placed on top of it, you can see it has an effective length of 3.2 centimeters. Now here's the wire we will use in the 4th trial of this experiment, and with the centimeter scale placed on top of it, you can see that its effective length is 4.2 centimeters. Now here's the printed circuit board for trial 5 in this experiment. This is a special circuit board, as well as the next one, double-sided circuit boards. Now the effective length of this circuit board is 3.2 centimeters on this side. The back of the circuit board is exactly the same length, for a total effective length of 6.4 centimeters. So here is the 6th and final printed circuit board that comes with this apparatus. This, like the previous one, is a double-sided circuit board, and when you place the centimeter scale on it, it measures 4.2 centimeters, but the back of the printed circuit board is exactly the same length, so the effective length of this circuit board in the external magnetic field is 8.4 centimeters. Now for part A of this experiment, trial 1, using the wire that is 1.2 centimeters, turn the current up to 2.5 amps, and you can see on the electronic scale that the deflection is 0.16 grams. Now here's trial 2, with a 2.2 centimeter long wire. Again, 2.5 amps of current, and you can see the deflection is 0.29 grams. Now here's trial 3 with the 3.2 centimeter long wire. You can see the deflection is 0.46 grams. Now here's trial 4 with the 4.2 centimeter long wire, and you can see the deflection is 0.63 grams. Now here's trial 5 with the 6.4 centimeter long wire, and you can see the deflection is 0.77 grams. And here's the last trial with the 8.4 centimeter long wire. With 2.5 amps of current, you can see the deflection of the magnet is 1.17 grams. Now with this information and the worksheet that accompanies this video, determine the relationship between the length of the wire and the magnetic force that it creates. Now in part B of this experiment, we use the same experimental setup, but instead of using a printed circuit board wire, we use Pasco's current balance accessory. Now this current balance apparatus allows us to change the orientation of the wire with respect to the external magnetic field. It can be changed from minus 90 degrees all the way through to 0 degrees, which means that the current running through the wires and the external magnetic field are both in the same direction, to positive 90 degrees. Now to begin the experiment, we lower the wire into the external magnetic field. Now in part B of this experiment, we're going to keep the current constant through the wire at 2.5 amps. You can see that on the ammeter on the left. And for trial 1 at minus 90 degrees, you can see the scale reading at -1 grams, which means that instead of the magnets being pushed down into the scale, they are actually being drawn up. Now in trial 2, we're going to change the angle to -75 degrees, and here is the reading on the scale for -75 degrees, and we'll just continue changing the angle by 15 degrees each time. So here's the reading at -60 degrees. And here's at -45. Here's the reading at minus 30 degrees. And minus 15 degrees. And at 0 degrees, the reading on the scale is 0 grams. And now at plus 15 degrees, the scale reads now plus 0.25 grams. Here's at plus 30 degrees. Here's at plus 45 degrees. Here's at plus 60 degrees. Here's at plus 75 degrees. And our last reading at plus 90 degrees. Now, with this information and the worksheet that accompanies this video, determine the relationship between the magnetic force and the angle that the wire makes with the external magnetic field.